I forgot to turn my microphone on, so I'm just going to have to narrate this. We'll see how it goes. It's not going to be live narration anymore. It's going to be narration after the fact. This next problem has two spheres. They're identical spheres. They're each charged with positive charge Q. So they're identical spheres. They have the same charge, so they'll have the same charge density. And you're asked to find the electric field at 4 different points. At point O, the origin, at point A, at point B, and at point C. The question is, can you use Gauss's law to do this, or are we going to need to integrate over point charges? Start it up right now, and then I'll show you the answer. So here's what you all answered. Main answer was that we're going to need to integrate. Probably you're thinking that this is a horrible charge distribution, but in fact what it is two spheres, both of which are great charge distributions, each of which is a great charge distribution for Gauss's law. If you want the total field, if you just know the field due to each of them, then you can add those vectors together. So the question is finding the field due to each of them at the point in interest, the point of interest, 0, A, B, or C. So suppose I chose C, the sphere on the left. I can, if I want to deal with the field at point C, I can draw a Gaussian sphere for the sphere on the left, a Gaussian surface for a sphere on the left that goes through point C. And I can use Gauss's law for that sphere to find the electric field due to the sphere on the left. That's going to point away from the sphere on the left. Once I have that electric field due to the left, I need the electric field vector due to the sphere on the right. And I can get that from Gauss's law also. The sphere on the left, by the way, this Gaussian sphere on the left has radius 2r, because that's how far the center is from point C, the center on the left. The center on the right is, okay, the 2r is the length of that. The center on the right, the center of the sphere on the right, is a different distance. It's 2r to the right of the origin and 2r above the origin. So 2r in the so that's the, I'm just writing out the electric field magnitude by Gauss's law from the field on the left, from the charged sphere on the left. That field is vertical, it's along the y-axis. So suppose I want to find the field at point C due to the sphere on the right. That field is going to look something like that. It's a positively charged sphere on the right, so it's going to point away from that sphere. And my Gaussian surface for the sphere, so get rid of everything here so that it's as clean as it can be. Although I keep erasing too much. The Gaussian surface through point C, centered on the sphere at the right, looks something like that. The distance to that Gaussian surface is the distance to point C is 2r to the left from the center of the sphere on the right, and 2r along the y direction, positive y direction, center of the sphere on the right. So if it's 2r to the left and 2r up, then the length of that vector that I've drawn there, that r vector, that little r vector, is the square of that length is 2r squared times 2. That's the square of the length. That's not the length itself. Sorry if I said it incorrectly in lecture. And then the charge enclosed is still Q, because the sphere on the right has the same charge. And I can calculate the magnitude of this electric field E sub r, the electric field vector E sub r. Now that's a different direction than E sub L, and so I'm going to have to use the geometry of the problem to find the angle and to find the total field. I can do it in components, E total along the x direction, E total along the y direction. And I can do that for any of the points. So Gauss's law works for each sphere, any point I want to choose, I can find the total electric field due to that sphere, both magnitude and direction. Since I have two spheres, at any point I'll have two vectors, one from each of the spheres, and that will, the sum of those two vectors will give me the total field.